All right, let's dive right into this. Welcome to our latest explainer. Today, we're going to take that familiar classroom poster you've probably stared at 100 times and transform it into a dynamic, living decoder ring for the entire physical world. Most of us look at the periodic table of elements and just see this static, slightly intimidating chart of letters and numbers. But today, we're going to learn how to read this thing for what it really is, the ultimate blueprint of the universe. Here is our quick roadmap for today. We'll start with decoding the periodic table. Then we'll look at metals, nonmetals, and metalloids. After that, we'll crack open the secret electron engine, followed by exploring the metal families, and finally, we'll wrap up with the halogens and noble gases.
So, starting off with Section 1, decoding the periodic table, the ultimate map.
Okay, so the modern periodic table isn't just a random assortment of building blocks. It's actually a highly intentional, meticulously organized map. It neatly divides up literally everything in our universe into distinct regions. You've got this massive expanse of metals taking up most of the real estate on the left. Then you have the nonmetals hugging the right side. And right in between them, separating the two, is this very specific, narrow staircase of elements called metalloids. And here's the cool part. Just by knowing which of those neighborhoods an element lives in, you can instantly predict how it's going to behave in the real world.
Moving right along to Section 2, metals, nonmetals, and metalloids, the three continents.
Let's start over in the metals neighborhood. Like we just talked about, the entire left side and the center of the table are completely dominated by metals. Now, at a chemical level, these elements typically have just 1, 2, or 3 outer electrons, and honestly, they are remarkably eager to just get rid of them. Because they lose these negatively charged electrons so easily, metals naturally form positively charged ions. Chemists call these cations. And that fundamental tendency, that deep desire to lose electrons, is really what makes a metal a metal.
But if we shift our focus all the way to the far right side of the map, we find the nonmetals neighborhood, and they operate on the exact opposite principle. They typically have 5, 6, or 7 outer electrons. So instead of wanting to lose them, nonmetals are greedy. They tend to snatch up electrons from their environment to complete their outer shells. By gaining those extra negative charges, they form negatively charged ions, which we call anions.
But nature rarely draws a perfectly sharp line, right? And that brings us to the metalloids stair-step. This distinct little dividing line features elements like silicon, boron, arsenic, and germanium. They sit directly between the metals and nonmetals, and their physical properties are caught right in the middle too. They aren't fantastic conductors like metals, but they aren't completely non-conductive like nonmetals either. Instead, they act as semiconductors. And that unique intermediate property is absolutely crucial. It's exactly what makes all of our modern computer chips and smartphones possible.
So the crucial point is this. When we compare their macroscopic traits directly, it's easy to see the difference. Metals are typically solid, shiny, and just fantastic conductors of heat and electricity. They're also malleable and ductile, meaning you can hammer them into sheets or pull them into wires. Nonmetals are basically the inverse. They're dull, poor conductors, and if you do find them in a solid state, they're highly brittle. Though, to be fair, they frequently exist as liquids or gases at room temperature anyway.
To truly understand why metals have those amazing flexible properties, why can a blacksmith pound a hot iron sword with a massive hammer without it just shattering into a million pieces, we have to zoom way, way down to the microscopic level. We have to look at the metallic bond in action. Picture these positive metal cores arranged in a rigid grid, but they're surrounded by this flowing sea of mobile electrons. Unlike other chemical bonds that rigidly lock atoms into place, the electrons in a metal are totally free to just swim around the positive cores.
I absolutely love the vivid way this principle is described in our source material. It says, mobile energies allow atoms to slide by like ball bearings in oil. It's a great mental image, right? Because that sea of negative electrons acts as a flexible, slippery glue. So when you strike a piece of metal with a hammer, the positive atoms don't snap apart. They just slide smoothly past one another. Literally, that is the secret to malleability.
All right, let's keep going. Section 3, the secret electron engine, core versus valence.
This brings us to probably the most important term for us to understand today, valence electrons. These are the outermost electrons of an atom. I like to think of valence electrons as the internal desires of an element. See, while the core electrons are tucked safely away deep inside the atom, the valence electrons sit right on the edge. They are the engine constantly driving the atom to interact, bond, and react with its neighbors in this never-ending quest for stability.
Next up, Section 4,
exploring the metal families. Meet the neighbors.
Okay, now we're going to zoom in on some specific families. First up are the elements in Group 1, sitting on the extreme left column of the map, the alkali metals. Take sodium, for example. These elements possess only a single valence electron, and the atom holds onto it very, very loosely. Because they only need to lose this one single electron to achieve a perfectly stable internal state, they are incredibly eager to just throw it away and stabilize into a +1 ion. And that utter desperation to lose that single electron makes alkali metals breathtakingly reactive. In fact, they are so volatile that you will absolutely never find an alkali metal just hanging out alone in nature. If you somehow manage to isolate pure sodium or potassium in a lab, it would instantly, and honestly often violently, react with the moisture or the oxygen in the surrounding air to form a compound. Now, if we move just one column over to the right, we meet Group 2, the alkaline earth metals. These guys have 2 valence electrons to give away, forming ions with a +2 charge. This still makes them highly reactive, but they're slightly less aggressive than their Group 1 neighbors. What's fascinating is how crucial these elements are to biology. Take calcium, for instance. It's an essential mineral nutrient. Literally, every time you drink a glass of milk, you are relying on the very specific chemical properties of this Group 2 metal to build strong bones.
Moving along, taking up that massive central block from groups 3 all the way through 12, we find the transition metals. Now, these are the elements most of us actually picture in our heads when we hear the word metal. They're harder, they're much less chemically reactive, and they are perfectly suited for construction, tools, and everyday items. Plus, they're famous for forming these beautifully colored compounds. It's precisely because of their stability and durability that transition metals, like copper, nickel, silver, and gold, are the exact materials humanity has historically used to craft our coins and our jewelry.
And finally, Section 5, halogens and noble gases, the extremes. Skipping way over to Group 17 on the right side, we have the halogens. Remember how the Group 1 alkali metals were desperately trying to get rid of one electron? Well, the halogens are their dark mirror. They have 7 valence electrons, meaning they are aggressively, desperately searching for just one more to reach a full outer shell of 8. This gives them a -1 charge. They are highly reactive diatomic nonmetals. And we actually harness that aggressive nature. Think about chlorine. It's so utterly ruthless at attacking organic molecules that we literally pump it into our swimming pools to hunt down and kill bacteria. And this brilliantly illustrates the final, ultimate truth of the periodic table. The impenetrable noble gas octet. The entire endgame of virtually all atomic bonding, every explosion, every bit of rust, every compound ever formed, is simply an attempt to reach the perfect, self-sufficient 8-electron outer shell of the Group 18 noble gases. Just look at argon. Because its outer shell is already perfectly full, it doesn't need to gain, lose, or share electrons with anyone. It has achieved atomic enlightenment. It's entirely self-sufficient, completely chemically inert, and highly non-reactive. Now, there is one tiny exception to the rule of 8, and that's helium, right at the very top of Group 18. Helium is so incredibly small that its outer shell is perfectly full with just 2 electrons. But the end result? It's exactly the same, total chemical independence. Because helium is both incredibly light and completely non-reactive, it's totally safe to use in everyday life. It's why we can effortlessly lift colorful balloons into the sky at a birthday party without worrying about them spontaneously catching on fire.
So, let's bring everything we've talked about today full circle. By looking at macroscopic properties, we can decode things right back into their elemental classifications. Say we're handed a mystery solid. If it conducts electricity, if it's malleable, and if it looks like a shiny sheet, we don't even need a microscope to know what it is. Because we now understand the elemental blueprint, we can instantly and confidently classify it as a metal. We can mentally visualize that sea of mobile electrons sliding past those positive cores, just by observing how the object behaves in the palm of our hand.
So, I want to leave you with this one thought. The periodic table isn't just some dusty poster in a high school science lab, it's literally the fundamental vocabulary of our reality. Just take a second and look at the objects around you right now. The glass of the screen you're looking at, the metal in your chair, the very air you are breathing. Based on their properties, where do their atoms live on the ultimate blueprint of the universe? Keep decoding, keep exploring, and I will see you in our next explainer.